Hello, my name is Carter Gillenwater. I am a master's student here at the University of Arizona. I did my undergrad in physics at Georgia Tech, and I now study optics here at the Wyant College of Optical Sciences. Today, I'm going to be demonstrating the laser waterfall, which uses the principle of total internal reflection. We're going to try and understand this principle using this demonstration. So here's a little preview of what we're going to be looking at. You have a 2-liter bottle that is filled up with usually water, but you can sometimes use other materials that are sort of a denser liquid. And you have a laser beam shining through it. And you can see that even as the water drains down and will continue moving backwards, the laser beam actually stays inside that column of water. So you might expect it would just continue on straight through and just pass through the water, as it's doing at the back here, but it actually is staying within that water the entire time. And that's what we're going to try and understand today. The first thing we have to know in order to get this to work is that light can bend. Here we see a ray of light coming into a block of glass, and you see that at this interface here, it's going to bend slightly, and then at the back interface, it's going to bend again. And you can see that actually this ray of light is parallel with this ray of light. It's just been shifted up a little bit. So why exactly is this happening? One way to understand this is the lifeguard analogy, which requires 2 more pieces of information. One is called Fermat's principle, which is the idea that light will always take the shortest path in time. So if it's going from point A to point B, it's going to try and find the quickest path between those two. The other thing to understand is that light will slow down in denser media. Now the reason for that is that if you have, say, air, the light will be hitting the air molecules and sort of bouncing around between them. And if you have a denser medium like water, there's more molecules closer together, and so the light will bounce around against more things and take a longer path. So effectively, the light takes longer in that medium, even though the speed of light is constant. So this is called the lifeguard analogy. And let's say that you are here on the beach, and you're the lifeguard, and you're trying to get to someone who needs help in the ocean. Now, you want to get there as fast as possible. So you're trying to think, okay, what's the quickest way I can get to this person to get them help? You might think that the easiest thing is to just run a straight line path, which is this one labeled A, the straight line from the beach, then through the water, to get to the person you're saving. The problem with this is that you know that you can run faster in air than you can swim in water. So you might think, okay, I want to go as far as I can on the beach before ever touching the water, and then swim a short distance so that you're not as slow. That might be path B, and then you take the shortest path within the water. The problem with this one is that now you're running a lot farther on the beach, so even though you're faster, you end up being slower overall because you're going a much farther distance. The best answer is actually somewhere in between these two, where you sort of run at an angle, and then you make a slight turn, and then you continue on in the water somewhere in between these two, and that's this path C. And this is essentially what the light is doing whenever it's trying to minimize this path. It's trying to find the shortest possible path. So this is a quick proof that's actually using mechanics. You can actually set it up using a mechanical system, and it will give you the same derivation.
So for this light into media problem, he imagines putting a rod on the border between the air and the water, and placing a ring on the rod, which is free to slide left and right. Now, attach a spring from the point A to the ring, and a second spring between the ring and point B. You can think of the layout of the springs as a potential path that light could take between A and B. To finagle things so that the potential energy in the springs equals the amount of time that light would take on that path, you just need to make sure that each spring has a constant tension, which is inversely proportional to the speed of light in its medium. The only problem with this is that constant tension springs don't actually exist.
That's right. They're unphysical springs, but there's still the aspect of the system wanting to minimize its total energy. That physical principle will hold even though these springs don't exist in the world as we know it.
The reason springs make the problem simpler, though, is that we can find the stable state just by balancing forces. The leftward component of the force in the top spring has to cancel out with the rightward component in the force of the bottom spring. In this case, The horizontal component in each spring is just the total force times the sine of the angle that that spring makes with the vertical.
And from that, out pops this thing called Snell's law, which many of us learned in our first physics class.
In our problem, light is trying to minimize time, but in this example, we're trying to use springs as an analogy to minimize energy, because the system will always tend towards the lowest potential energy, and it ends up giving you the same result. And that result is called Snell's law. And so here we've rewritten Snell's law, having that sine of the theta in each of the medium. So here this yellow is representing the air, and this blue is representing the water, and this is the surface in between those two. So you can see the light is coming in and hitting the water at an angle, that angle being called theta 1, and then when it bends, also called refracts, into that water, that angle in the water will actually shrink because the velocity in the water is slower, and so the angle in the water will also be slower, or it will be smaller. And here we can see that we have that same equation as before, except we can make one quick change where we multiply each side by c, which is the speed of light, and then we can call this value the speed of light in vacuum divided by the speed of light in whatever the medium is. We can rename that as n, which is often called the index of refraction. And one way of thinking about it is essentially a measure of the optical density of whatever your medium is. And so you rewrite Snell's law as the value of the refractive index times the sine of the incident angle, the angle that the light is coming in, is always going to be constant no matter what these two media are. So there's no actual reason why the light has to go from the air to the water. We can do it in reverse. We can say that the light is actually coming from the water to the air. And so it's the same principle. The great thing about light is that you can just play it in reverse and everything still works fine. So it's the same thing as before, where inside the water, this angle is going to be smaller, and then in the air, the angle is going to be larger. And you can sort of imagine taking a laser pointer and shooting it at this surface of the water, and taking that laser pointer and changing the angle. And as you do, you take that angle and you make it wider and wider, closer and closer to the water's edge, and eventually you'll get to a point where this theta 2 will get so low, it will actually be parallel with the surface of the water. At this point, it is called the critical angle, this theta here. The critical angle is the point at which no more light is coming into the air. All of it is going to be bent downwards, either parallel to the water, or if you go beyond the critical angle, you make that angle even larger, you get to the point where not only is it parallel to the water, but it's actually reflecting back into the water. And so that is what total internal reflection is. It's total as in all of the light is being reflected internally inside the medium of the water. Though it's a requirement here that the optical density, the index of refraction here, is larger than it is above. And if you have that principle met, you can display this total internal reflection. Here's a set of just a few examples of total internal reflection that's used in real life. One of them is, for example, a pair of binoculars. So you see that here you have one large lens that's actually taking in the light, and then there are two prisms within the binoculars. And inside of those prisms, the light is totally internally reflecting, and will go through both of those prisms and bend back towards where your eye is. Another related example is there are some artificial reality goggles. You may have seen some of these. And in order to have the glass in front of your eyes be transparent, but you want for artificial reality for there to be an image on top of whatever you're looking at. What some designs will use is they'll have light totally internally reflecting inside those goggles, inside the lens there, and it'll be projected from up above and then sent into your eyes so that you see both the real world through the glass, and you see whatever the image is you're looking at on the glass itself. So they're sort of overlaid, and it can kind of trick your brain into thinking that seeing what your image is inside the goggles, you're tricking your brain into seeing it in reality. Another really big example is optical fibers. This is used all the time in the study of optics. What you may have heard of it is as fiber internet. So there's a lot of people who you may even have fiber internet. It's being rolled out in a lot of places. The way that this works is you essentially take that idea of total internal reflection and you have everything be made into a cylinder. So you have your denser medium on the inside, and then you have a slightly less dense medium as your cladding or the cover that's on that fiber. And what you get is that if you put in light at a certain angle, you will get total internal reflection even if you bend that fiber. And so it'll reflect all the way through. And the important part is that you're not losing any information while this is happening. So this wire, this fiber, could in theory be miles and miles and miles long, and you can still transmit light down it and receive that light at the other end. Now, that's really only useful if you can send down useful information through it. So what you do is you send pulses of light in the same way that you might think of sending like a radio signal or electrons through a copper wire. It's the same idea. You send light down it, and you encode a signal in that light. And so if you're thinking about like a transatlantic cable, where if you're watching, something on television from the other side of the Atlantic or the Pacific, then that would be coming through an optical fiber that's been laid underneath the ocean floor and can send tens of thousands of signals constantly, and then you can get that signal on the other side without losing any of that information. Another example, a lot of smartphones recently have been getting these really, really good fingerprint scanners, and if you're like me, some of them have an optical fingerprint scanner. If you go ahead and press your finger on that fingerprint scanner, it will actually send out a flash of light from underneath the screen, and your fingerprint will actually, as you press onto the screen, will change that local environment, and it can actually tell where the ridges and bumps of your fingerprint is when that light flashes onto it, and then it can actually take that reflection and measure your fingerprint very, very accurately, and then it can determine you are the person who's trying to unlock that phone, and it'll open the phone for you. Another example in medicine is called an endoscope. This is essentially a camera at the end of a very long tube that can be put inside the human body to look at things internally that might require surgery. This is a lot easier than actually opening somebody up. You can use this camera to see certain things. Now, it's sort of difficult to fit a full camera system inside of a human body, especially if you think about like an artery that's very, very thin. But here you actually have a bright light at the end of this tube, and then that camera signal is being sent through that tube with total internal reflection. And then at the other end, the doctor or nurse can look at it through this little camera at the end of the tube, or they can put it onto a monitor and they can see what's going on a lot more accurately inside of you without having to do any sort of intrusive surgery. Finally, if you've ever seen a heads-up display inside of a car, there are some performance cars that might have these. Some of them are a separate piece of glass, and some of them will actually project onto the windshield. And what's happening here is this sort of similar to the AR glasses, where it's a type of glass that's being completely transparent, so you can see the road through it, so it doesn't obstruct your vision. But there are signals being projected from underneath that glass, and it's reflecting inside of that glass, so it actually sends the signal into your eyes. There's tons and tons of applications. These are just a few examples that you may have heard of before, but it's used all the time and a lot in optics research. And so now we can finally move over to the demonstration here in the laser waterfall. So the idea here is we're going to take this bucket of water here, and I have a small, very smooth stream coming out of it. And then we're going to unplug this, and I'm going to take my laser pointer and shine it through the back end here. And you may be able to see in the bottom of the stream there, you can see that the light is actually staying within the stream. And you can mainly see it at the bottom where that radius of curvature is higher, because more of the light is going to be escaping there and is also probably reflecting from the surface of the water. And you can see as I change the angle very slightly at the input here, changing the laser input, it will actually affect how much light is going into this stream here. And you can even see there that it's actually reflecting on the bottom of the bucket. So not only is it continuing through the stream, but it's actually bending the light so it's now facing straight downwards. And you can see even as this stream gets lower and lower, the light will continue to stay inside the stream throughout. And there you go. So that's just our little toy model of total internal reflection. And thank you very much for listening.